So good morning, everybody. So I think it's time to get started. So my name is Eric Auger. I work at Red Hat in the virtualization team together with Alex and Cedric, for those who attended the vfio meeting, the vfio presentation just before. And I'm also the vfio-platform driver sub-maintainer. And I decided to submit this talk because I want to bring up the fact that for some time we have some trouble testing vfio platform with upstream bits. And so to me, it deserves some discussions, and that's the purpose of this talk. So let's start with some context. So actually, 10 years ago, the topic was quite popular. So we had some presentations at LPC, at KVM Forum. I made my first presentation at KVM Forum 10 years ago about this topic. And at that time, we had some real interest from big ARM players like AMD. So we had a significant upstream effort done. In 2015, we got the vfio platform driver upstream. It came along with two 10 gigabit Ethernet devices being officially integrated, and I will explain what it means. And at that time, also, we got the QEMU vfio platform device upstream. So this was the first integration in a VMM. And then, so this is my actual point. So the last integrated device was in 2017 with the Broadcom FlexRM mailbox. And the last functional kernel contribution was in 2018. It was related to some experiments related to the Renesas Aircar Gen 3 platform. And Geert Witthoven, so I'm not sure I pronounced the name correctly, so made some contributions related to that, tried to assign some devices like GPIO controllers, and also he contributed the dynamic power management in the vfio platform driver. But that's basically it. And besides that, so we know that vfio platform is used. We know that internally because we have some requests to enable the config and so on. But the problem is that it is absolutely not transparent. We have no upstream contributions. And I will try to demonstrate that we should have some upstream contributions. And it is up to the point that now we have a trouble because if you consider the dates above mentioned, so those systems have been e-wasted. So we cannot test anymore with upstream bits. So I was forced recently to resume working on integrating a new device because we had a CV at vfio subsystem level, and we need to test some stuff also at vfio platform level. It was related to IRQFD handling, and I was not able to test anymore. So I resume integrating a new device, and I will show examples related to this new integration. So the goal of this talk is to remind that vfio platform exists. So this is my first goal. I want to re-explain what it is used for and what it is not meant to use for also. I want to explain how to integrate a device, because maybe we have not made sufficient effort to explain that. So I want to make sure that everybody understands what is needed. And at the end of this talk, I expect that, I hope that we'll understand the main challenges doing a device integration and try, and I hope you will be able to understand if a device is a good candidate to be integrated in the vfio platform, or there are too many showstoppers that would guide you against doing this kind of integration. And I hope we will have time to start some discussions on the fate of the vfio platform in general, because we saw that there is a lack of upstream contributions. And maybe we won't have time during this session, but afterwards. So let's start with the goal of vfio platform. So I guess for most of you are already familiar with vfio PCI. So it is the same principle. So it gives user space control over a physical device, but this time this is a platform device instead of a PCI device. A strong assumption is that there is an underlying physical IOMMU, okay, because it reuses all the concepts that Alex explained before, so IOMMU groups, containers, and so on. So it's really tied to an IOMMU. And generally, you put devices upstream to an IOMMU when they are DMA-capable devices, because otherwise there is no much gain. So that's a really important assumption. So then the user API gives you the ability to have a direct access to the registers of the device, so instead of bars and configs. It allows you to forward interrupts and handle them at user space level. And eventually, so you have the capability to map DMA buffers to user VAs. So it's also tied to the IOMMU. So in terms of use case, so what is first targeted is the capability to write user space drivers instead of kernel native drivers. So it typically targets DPDK like use cases. And besides that, so you may be interested to assign the vfio, the platform device to a guest. So it's a more advanced use case. And this is what allows the QEMU framework, for instance. In terms of hardware platforms, so currently vfio platform is supported on ARM. And I would say that we mostly target embedded, automotive, and edge platforms. So not servers, because if you have a PCI topology, so you would prefer to assign PCI devices. So this is mostly targeting SoCs which have no PCI access, but sometimes I will share the example of the NVIDIA Jetson Orin system. It has PCI, but it also allows to expose some platform devices. So then I will describe what is needed to support a new device. So I told you currently we have 3 officially supported devices at both kernel and QEMU level. So those are pretty old devices, as you may see. And actually, it's not like vfio PCI, where you can directly use it out of the shelf, except maybe the new variant drivers that are needed also, that require some adaptation. For vfio platform, you need to do some adaptation at both kernel level, because you need to support device reset. And if your use case is to expose the device to a guest, you need to add some piece of code in the VMM to expose the device to the guest. So let's first have a look at the device reset problematic. So the trouble is that, so I think it's quite natural to understand that when you assign a device to a guest or a user space driver, you need to be able to reset it. So, for instance, if you assign it to a virtual machine, what may happen is that the virtual machine crashes, and before it has programmed the device to perform some DMA request or to send interrupts. And the problem is when it crashes, so all the IOMMU mappings that were used to translate the DMA request are destroyed, so there is no risk. But when you start again a VM with the same device assigned, the mappings, the IOMMU mappings are created, and you expose the whole VM RAM to the previous DMA request. So that's the danger, and it will jeopardize the integrity of the new virtual machine. So what you need to know is to be able to stop the DMA transfers that were initiated. You need to disable the interrupts. And in some cases, and we will give more explanation about this need, you need to get and put some dynamic resources that are vital to get the device functional. The problem is that, as opposed to vfio-platform, vfio-PCI, sorry, you have no standard way to reset a platform device. So there is no specification. It can be in registers, it can be reset pins and whatever. So, and vfio-platform driver itself is totally device agnostic. So it has no clue about what kind of device it mediates in terms of control. So we have two solutions to handle device-specific reset. So it depends on the type of booting. So in case you boot with a CPI, so we can use the RST method. So this is currently used with the FlexRM mailbox. So you have an example. And but until now we have mostly covered DT boot. And in that case, what you are using is a custom reset module in the kernel. And this is what I'm going to focus on in the next slides. So you must know that there is a module infrastructure, a kernel reset module infrastructure already in place in the kernel. So what you need to do, if you write a new reset module, it will be automatically loaded on device attached using the device compatibility string that is used for this device. And this reset module is supposed to implement a single reset method, which is called by the main vfio platform driver on open, close, and on device reset IOCTL. This is how it is done today. So you will find at least 3 examples in this directory in Linux. So in terms of challenges when you write a new reset module kernel, is that you need some knowledge about the device. You need to understand how to reset it. So if you look at the examples available in this directory, you will see that those reset modules are quite simple. Basically, what it does is it picks and pokes some registers which are related to reset. So it enables, it disables interrupts, it disables the DMAs. So it's pretty simple, it's pretty straightforward, I would say. Now it can become more complex, and this is what I'm going to explain. It can require some dynamic resources like clocks or resets, and this is not yet covered by the current implementation. So I told you I was forced to integrate a new device, so I chose that one. So the Tegra 234 multi-gigabit Ethernet controller from the NVIDIA Jetson Orin board. And this device is quite interesting in terms of integration because it pushes somehow the limits we already experienced before. So there is an RFC that is available at kernel on the kernel mailing list. So you can have a look. So what is interesting with this device is that it requires some dynamic resources. So it requires clocks and reset. And as I explained before, so originally we didn't need that because the devices we integrated before were simpler. And in that case, what I needed to add is 2 new callbacks besides the actual reset function. One callback which is called on init, and the other one which is called on release. And the job of the implementation of those callbacks for the Tegra 234 MGB reset module is that they are going to get and prepare the clocks and get the resets. So you make sure that all the dynamic resources are there before giving access to the VM. So this is new, and so I hope this will get some traction on the Linux kernel list. Kernel mailing list. And so logically, it should allow the integration of new and more complex devices that require dynamic resources. So we talked about the integration, the adaptation needed at kernel level. So if your target is just to write a user space driver, so it's sufficient for you. But if you want to expose your device to a guest, so you need something more. So this time you need to do some adaptation at the VMM level, because the problematic is that for platform devices, you have no PCI-like bus enumeration, so it's not enough to expose the platform device to the guest, so the platform device object. You need to write a description what this device looks like in terms of SCPI or device tree. So in that case, I will mostly focus on device tree aspects, and I will give you some examples. So there is currently a QEMU integration for vfio-platform. So the principle actually is that when you pass this option to the QEMU command line, targeting the assignment of this Ethernet controller, so behind the hood, QEMU uses what is called the dynamic sysbus instantiation. So it uses a so-called platform bus, and then it creates the vfio platform device and plugs this vfio platform device to the platform bus. So there are helpers already in place that find the right MMIO slots, the interrupt slots, and it connects all that stuff transparently to the interrupt controller, for instance, and so on. So you do not need to care about this QEMU object topology. This is done for you. But what is needed is to take care of the device tree generation, because this is purely device specific. And this code can be found in this file. And you will have at least 3 examples today, so for the 3 integrated devices. And there is a new proposal for the Tera 234 MGBE also. So the principle is quite simple. So you have a binding structure that associates for each compatibility string a device node creation function. And so QEMU looks at the device you want to attach, is able to fetch the capability string, and knows that it needs to call this function to create the device tree representation of this device. So here is the first device we integrated. You can see that the device tree node is really simple, just 4 properties. So the register properties that tells which registers are exposed, the interrupts, compatibility string, and the DMA coherency property. So what you need to do, so this is the device tree node on the host. So you need to create basically the same stuff on the guest. Okay, but we have, so in the sysbus.dt file, you have helpers. That will help you to locate the address the device was put in on the guest side. You will be able to retrieve the size of the regions, and you will be able to retrieve also the SPI interrupt the device is plugged onto on the guest side. So it's fairly easy to build that device tree node on the guest. So I would say this one was really vfio platform friendly, very simple device tree node. So it was a fairly easy job. So now let's have a look at the second device we integrated. So you will find exactly the same kind of properties we described before, but this time, so we have plenty of device-specific properties we need to generate. So for those, so what was done actually, we are fetching the values of those properties on our side. We are copying them and pasting them on the guest device tree node. So it's quite easy as well. But you need to understand, when you do that kind of job, you need to understand the properties. So there is some knowledge needed. So it's not like plugging a vfio PCI device. So you need to look at the binding descriptions and so on. So this is the kind of job you need to do. So the additional challenge we had is to handle the clocks property, because here you can see some reference to external clock nodes. And the problem is that you will need also to generate those nodes on the guest side. So it becomes more complicated because you don't have a single node anymore. You need to generate some providers for some resources. So it's obviously more complicated. But it was fairly simple in that case because we were lucky enough that those clocks were stable. So fixed values, fixed clock property, meaning that the clock frequency is stable and we can just copy the nodes that you can find on the host and copy them on the guest. So hopefully this was quite easy. So now let's have a look at the Tegra 234 MGBE. So this is the next level. It gets much more complicated because on top of the previous properties, so you will find also clocks and so all the stuff we described before, but now you have resets. You have interconnects, you have power domains, you have a phi handle, p handle, and you have a MDIO sub-device. So it starts to be much more complicated. So luckily, so this is an experiment today because so it's an RFC on the QEMU side. I was able to get rid of some of them which are not requested from a binding point of view. If you look at the documentation in Linux, for instance, interconnects, this is not a mandatory property. So I got rid of that. I got rid of power domain, but yeah, I was cheating on that one because so theoretically this is mandated. But so in practice, the guest is happy with that, at least for the moment. For the phi handle, I got rid of it, but it is requested also at the moment. The MDIO stuff is not requested, so I got rid of it. However, the reset is not optional. So if you don't expose any reset on the guest side, it won't probe. So the device won't probe. So you start crying because in that case, what you need to do is to generate a reset controller DT node on guest side. And if you look at the P handles that are used in this device tree node, so it refers to what is called the BPMP. This is a specific IP on the Tegra hardware that manages all the resources like reset, clocks, power, and many more. So, and the problem is that you cannot expose that to the guest because it drags other dependencies. For instance, you need a mailbox, and without, so I try to expose this mailbox to the guest, but it requires some emulation because it tries to read some registers when probing, and if you don't have this register, it fails. So the only solution I found is to use a iSilicon reset controller, which has another dependencies on the syscon device, but this one probes gets probed properly, so it's not a problem. But so it's somehow the same problem as clocks. So you expose some stubs on the guest side, and so you see the limit of this technique, because if the guest tries to use those resources, so it may have some consequences. So eventually, here is a representation of associated to this node that I was obliged to expose to the guest. So as a conclusion, so there are definitively some showstoppers when integrating a new device. So if you try to assign a GPIO controller or something like that, just to blink LEDs, there is no IOMMU, so it will be rejected, and we are not supportive of such use cases. There is another issue if you have dependencies to DMA controllers, in which case the DMA controllers have a relationship with the IOMMU, and it's more difficult it won't be possible to assign the device. You would be obliged to assign the DMA controller itself as a whole. So we have seen that I expose some DT node stubs to the guest, and sometimes it won't work because you need some emulation. So there are some issues if you have shared resources also. If you share a reset with another device which is used by the host, it's a problem. So those are showstoppers. Now, what can be troublesome is dynamic resource management, but we should be mostly okay with the extensions in the reset module. And it's hacky, I would say, to generate stubs on the guest side. So this is something problematic. And sorry. And so also you need to be aware that the native driver maintainers should be in the loop because it requires knowledge about the device. So you need to have their hack when you do such kind of exercise. So they must be in the loop. And it's a problem also in terms of maintenance. Okay, so what would be really helpful is to have virtual functions. Because if you get some virtual functions, even on platform devices, it will reduce the dependencies on external resources, on external resource providers, because the physical function will handle those and will simplify a lot the description you need to make on the guest side. So this is really, I would say, the future if we really want to use simply vfio-platform to assign to a guest. So now I come to the actual discussion. How many minutes do I have? 5 minutes, so it won't be sufficient. So besides all the difficulties we have seen before, I don't think this is the actual problem because we are all engineers, and so I think we can fix solutions, find solutions. But the actual question is there a real market segment for vfio platform assignment? So there are some customers, but it's unclear what they want to do. And also, we would like to see some concrete contributions upstream, because so the reset drivers are mandated. Maybe the rest we can ignore what they do, but the reset modules are mandated. And if we don't have that, to be honest, there is a high risk of driver deprecation because we cannot test it anymore. So of course I can maintain an out of tree integration, but is it my job? I don't know. So it's questionable. And the last word is that so I'm totally willing to help for new device integration. If there is a real market traction for some device to be integrated, I will be glad to help. So Alex.
Was that obvious? Awesome, great. First off, I'm happy to kill it. I was the biggest proponent of this whole vfio platform 10 years ago. It didn't take off. It was an experiment, fair enough. A couple of comments. You're cheating a lot, right? Especially when it comes to clocks. Not all devices are happy with fixed clocks or happy with just a simple reset type of logic. Yeah. So if you would try to go and do the same thing with, for example, an MMC, like an SD controller, all hell would break loose. Like, you wouldn't be
totally
able to
agree.
talk to any device.
And this is what you told in 2013 in your LPC presentation. So I'm not surprised about that. Effectively, if some drivers need to actually set the clock frequency, you are dead, or you need emulation. And I mentioned the interconnect property also. It's set to constrain or to ask for a given bandwidth on the subsystem. So this is the same kind of... so at least, so that's true. I'm cheating in many places. Maybe this is acceptable for some use cases. I don't know.
No, the whole point of this exercise of merging the hacky code and getting that going was to tap the foot into the water and see whether there is actual desire to go and improve going forward. We haven't seen any. Yeah. Like, all the devices that ever were used with this are pretty much dead at this point.
Yeah, totally.
There is just simply nobody that cares. And if they do care, then we can remove this and then have them resubmitted upstream with a sensible modern interface and architecture. So what we would need to do is we would need to basically adopt Alex's variant mechanism, where you don't have reset drivers, you really have specific vfio platform X drivers, right? Then the next thing you would need to do is these drivers would need to implement generic, more or less generic interfaces into user space that give you access to what effectively the kernel APIs for setting clocks, performing a reset, all of these APIs, but safeguard them, right? Make sure they're actually safe. And then we would need to implement PV, clock setting, PV, power domains, PV, any of these things, so you don't have to expose a high silicon device into a random board, right? So all of these would then become PV drivers, and that's a lot of work.
Yeah, that's actually the question. So is it a real market traction to do all that stuff? So if people want to keep the functionality, they need to contribute also to that.
The easiest way to find out is by removing the code. And if somebody shouts, you tell them, happy for you to be the new maintainer. Go and, like, we have a list of things you need to do. Please go and resubmit with this new
but actually, this is what we plan somehow to do. So if we are not aware of any...
Kill it. Now.
Okay, so it's an interesting discussion and outcome.
Just kill it.
Thank you. Any other question?
Fortunately, we are out of the time.
Yeah, sorry.
Thank you.
Okay, thank you very much.